on the remainder of modular forms. So standard notations, H is going to be the upper half plane. Gamma is a subgroup of finite index of SL2 of D. So for G matrix A, B, C, D in Q, and F a map on the upper plane to C, one set F slash G of Z. So by definition, this is the determinant. I think the rule is to the power k over 2. Of course, if G is in SL2 of this, is determinant is 1. And you take CZ plus D to the power of minus k times f of AZ plus B over CZ plus D. Okay, I want this to be a positive determinant. So that AZ plus B over CZ plus D is still in the upper plane. And I didn't tell you what k is, so k is an integer, fixed integer. Okay, so those are the standard definitions. And mk of gamma, by definition, this is a set of functions from the upper plane to C, which are holomorphic. And which are invariant under gamma. In gamma. And there is another condition. If you take f slash h, and you look at its value on the imaginary axis of the upper plane, this goes to sublimit. When y goes to infinity, and this has to hold for every h. Of course, the limit depends on h. In h integral to q. Okay, so this is not a very important one. The essential condition is, of course, the invariance by gamma. And the limits would depend on h, so let me call it what? CH of F. So this is a space of holomorphic modular forms with k for gamma. So the thing to be aware of is it's a finite dimensional vector space, which can be identified with space of differential forms, element surfaces, if you want. And inside there is a not much smaller subspace. M is form modular, S is for Spitzenform, the German word, which is the set of F in NK of gamma, such that CH of F equals 0 for every H. Okay, that's the space of Gus forms. Of weight K for them. Actually, we'll be interested only in two kind of subgroups. Gamma node of n. So n is still this prime number I introduced at the beginning. Gamma in SF2 of Z. So that gamma is congruent to mod n. And inside, you have a subgroup of finite index, gamma 1 to n. That gamma is congruent to 1, 1, 0. Okay, so upper triangular mod n and unipotent mod n. Of course, it's not very difficult to see that if you take this is a normal subgroup, gamma 1, gamma node of n, modulo gamma 1 of n is isomorphic, in fact, to, well, in fact, the correct definition would be plus or minus. Doesn't matter much. And so this is Z mod NZ, star modulo plus or minus 1, and which to A, B, C, D. N, for instance. Okay, so you have this identification. Now, if you take a modular form, so the matrix 1, 1, 0, 1 belongs to gamma node of n, and also to gamma 1 n. And so, because of the functional equation satisfied by f, which is on the upper board on the right, f slash the matrix 1, 1, 0, 1 is equal to f, and therefore f is periodic of period 1. So f admits a Q expansion. So n equals 0. Okay, yeah, n equals 0 to infinity of a n q to z. You can write it that way, where q is exponential to I by z. So that's a Q expansion of a modular form. And F is a cusp form. Not immediate, but that's true in that case. F is S2 of gamma node of n, if and only if a node, a node of F is equal to 0. one modular form you can, for every L, there is one specific modular form called an Eisenstein series. It's defined as follows. It's not a curse form, so it has a constant coefficient. And the constant coefficient is essentially something we have seen already. It's n minus 1, not over 12, but over 24. And it has other coefficients. So from n equal 1 to infinity of, let's call this sigma 1 of n. The classical notation in sigma 1 of n is the sum of the divisors of n. But in that case, I have to introduce a slight modification. I take the divisor of n, which are co-prime to capital N. So those are sum of d divides n and d co-prime to capital N of d. Okay, so in particular, and this is important, when little n is a prime number L, sigma prime 1 of n is in fact simply L plus 1. Prime number not equal to 1. Okay, so this is the Eisenstein series. So the Eisenstein series can, in general, be put nicely into families, like this. But as for the curse form, generally they cannot be put into families. They are really discrete objects. So the fundamental structure on the space of modular forms is that there are a number of operators then, called Hecke operators. So it's n in Hecke. So you've got the Hecke operator T and tilde. Hecke operator. And it acts on the space of modular forms. Well, you can put gamma naught or gamma 1. So gamma naught will be enough. I'm not going to give you the definition. I'm going to give you the main property of Hecke operator in the following way. Such that if you take the first coefficient of Tm tilde acting on the modular form f, then you get the nth coefficient of f. For capital property of Hecke operators. And so those operators commute, so Tm's commute. And they span a subalgebra of the ring of endomorphism of M2 of gamma naught of n. So span T tilde the Hecke algebra. Which is contained in M2 of gamma naught of n. Okay. fact, the Hecke operator leaves stable the space S2, the plus forms, and denoted by Tn is Tn tilde restricted to the plus forms, and T, the Hecke algebra, is T tilde restricted to the plus forms. Okay. Another thing, an important thing, is that a priori, the space of modular forms are complex vector spaces, but there is a natural integral structure of them. So let's call M to Z. Yeah. Yeah, you can state it that way. There is a non-degenerate pairing on both sides between M2 cross tilde toward C, theory, which to modular form F and the Hecke operator T associates A1 of TF. And so this is non-degenerate on both sides, as I said. So then you deduce from that an identification as the space of modular forms is nothing else than the dual of the Hecke. This is a group of morphisms. Okay, so that's one way, and similarly, of course, there is a tilde here, and similarly, the plus forms are the homomorphism of the smaller space of the smaller dual. So the essential things are not those complex valued functions, but rather the Hecke algebra itself, which is a fundamental object. And in particular, if you take A, any group, abelian group, you can define, well, I suppose it's not the proper definition, but for us that we do. A as simply the homomorphism from the Hecke algebra. And similarly for S2. Okay. So in particular, those elements have Q expansions with coefficients in A. And what is interesting, if you have erased the definition of the Eisenstein series, but if you take A to be, let's say, Z mod N-1/24, Z, you can see that the Eisenstein series, you can still see it here, in that group has a constant coefficient, which is in fact 0. becomes the plus form if you go to the coefficient in that particular form. Okay. As this is really the great discovery of Barry Mazur in his 1977 paper, the Hecke algebra has a very special ideal. And this is the Eisenstein ideal, the title. So what is the Eisenstein ideal? And inside you have so it is spanned. Okay, so you want to impose that the eigenvalue of the Hecke operator TL. So you want to impose that the Eisenstein ideal destroys the Eisenstein series. So in particular, the nth coefficient of the Eisenstein series should be the eigenvalue of the nth Hecke operator. So that leads you to the following definition. So you want in particular that the Hecke operator TL acts like L plus 1. As I said, the L's coefficient of E, the Eisenstein series E2, is L plus 1. So for L prime. Okay, and L not N. Okay, so there is an additional operator, but it doesn't count much. It's 1 plus Wn. So Wn of f is f slash 0 minus 1 and 0. So it's an involution. But don't worry about what it does. Okay, so both versions of the Eisenstein ideal are actually spanned either by this or by Tl. Okay, so now you have this ideal. Since every Hecke operator likes like integer, then you have a map. One derives that T tilde mod I tilde is isomorphic to Z. TL associates L plus 1, of course. And as for the other quotient, you get a finite group as a quotient. And the finite group is essentially n minus 1. It's n minus 1 over 12, once again. By n minus 1 over 12, I mean actually the numerator of n minus 1 over 12. And so this is due to Mazur. So you know the ring modulo the ideal, and the next step is to know the ideal modulo the square of the ideal. For example, Mazur again. If you take I modulo its square, this is isomorphic to Z mod n Z star modulo the 12th root of unity. Which is obviously the same thing as the pass to the 12th power. This is the same thing with the 12th power of Z mod NZ star. And how is this map given? This is the Eisenstein ideal. It is generated by elements of the form Tn minus L plus 1. And so Mazur came up with a formula, which is the following one. Mod N. So we call that N is prime. And actually, there is a little exercise of checking that this is in fact well defined, which is not obvious because you have a square root here, but it's still well defined. Okay, and you have this identification. So here is another description of square root of u. This is what actually yes, this is almost a definition of that Mazur gave for square root of u initially. Well, not quite, but almost. Square root of u is okay. Yes, square root of u is the image of. So recall where we are. We said that T mod n is isomorphic to this group. This is the numerator of n-1/12. Consequently, little n belongs to I because it vanishes in that group. So n belongs to I, and therefore it has an image modulo I squared. This image is something well defined into this group. And the image is precisely the image of n in I over I squared, which is isomorphic to z odd nz star modulo, well, the 12th root version, or 12th power version. Okay, so this is the modular form approach to this element. And there are consequences of the structure of the Hecke algebra, namely this one. How much time? 15 minutes? About 15 minutes? Okay. So consequences. The consequences were formulated initially by Mazur. If you take T prime, which divides the numerator of n-1/12, and consider the maximal ideal P, which is the Eisenstein ideal plus P for T. So it's a maximal ideal of T. Then TP, which is a PLD completion of T. Then this is a ZP, the ZP algebra. And so what Mazur noted back then is that TP is isomorphic to ZP if and only if square root of u is a piece power. Okay. Okay. So now I should, so this is mathematics from 1977. I should tell you more about current mathematics. In the last 15 minutes. So you can understand the square root of u in terms of the Einstein series in the following way. So there is a map. So I mentioned this other group, gamma 1 of n, when I started on modular forms. So you've got a map. And I said that the gamma naught of n modulo gamma 1 of n is z mod n z star modulo plus or minus 1. So you've got an action of z mod n z star modulo plus or minus 1 of this space in the following way. By if you take G, you take G an element of the D is D. And here you take a modular form F, and you associate F slash the matrix A, B, C, D, and A, B, C, D is supposed to belong to gamma naught. Okay, so this is how you can define this action. And there is another connection between the space of modular form for gamma 1 of n and the modular form from gamma naught of n. So since gamma 1 of n is smaller than gamma naught of n, obviously this space is a subspace of this one, but you get a map in the other direction as well. And this map is given for any coefficients here, and this map is given by the trace, so namely which to F associates sum for D in Z mod n Z star modulo plus or minus 1 of F, F slash D. So you take the trace. Okay. And this map is actually surjective. And this map also respects the space of closed forms. But it is not in general surjective as it's said. Okay, so you've got this map, and you can do the following thing. Sigma is a map which goes from S2, A, toward, okay, Z, which towards Z, mod n Z star, modulo the 12th root of unity, and given as follows. If you take an element here, so let's call it a trace. It's a trace of something, but something which might not be a cos form. So it has to be, could be the trace of something which is holomorphic, but not a cos form. Trace. And this G1 has a Q expansion and has, in particular, a constant term. So to F, you associate the product D in Z mod N Z star to plus or minus 1. You take the constant coefficient of G1 to which you apply D by this map. No, it's not that. It's D to the power D to the power of A naught of G1 slash D. Okay, so that's the rule. And you can do the same thing with if you replace the coefficient Z by any A, simply you have to tensor by A at the end. So you've got this map. And so the fact I'm going to mention now. So this was essentially considered by Paris and Venkatesh fairly recently. So Paris and Venkatesh have studied certain arithmetic equations as part of the very general conjectures of Venkatesh, and in particular they had to consider this thing. So in particular, if you want, you can replace Z by A here. So that becomes A. And the recipe would be in that case. And then A naught would be in A. So that would be D. Tensor A naught. That would be the formula for any abelian group A. And in particular, if A is, as I said, Z mod NZ, then the Eisenstein series becomes the cos form, and it's meaningful to take the image of the Eisenstein series by sigma. And then sigma of E2 is precisely square root of U. So this is another way of recovering this number. Okay, so how can one go beyond this? This is what we are Emmanuel and myself, Emmanuel Couturier and myself are working out now, especially around the conjectures of Paris and Venkatesh. So I'm sure he will tell you more when he will be here, but I can already tell you something. And 5 minutes. Okay, so here's the philosophy now. If you recall that we have the Eisenstein ideal here, I, if you apply it to M2 of gamma naught of N, or theta, let's say, you get actually the cos force over any base. Now, you might wonder about what is the kernel of sigma. This is precisely I S2 of gamma naught. Okay, and so if a modular form belongs to the kernel of sigma, you can still define sort of a higher invariant. So initially, you see the fact that a modular form is in I tilde kind of space of closed form is simply controlled by the constant coefficient. So it's a vanishing of the constant the fact that the modular form is in that subspace is controlled by the value of sigma. So now you can go further. So there exists sigma I, so a set of maps. And sigma I goes to the ith power of I. Towards Z mod n z star modulo the 12th root of unity to the tensor power R. And how it is characterized? By sigma I of, okay, so L minus L plus 1 F is equal to sigma I minus 1 F tensor L to the power of L minus 1 over 2 for every prime L. Okay, so sometimes sigma, the letter sigma is for Shimura, and so this is sometimes called the Shimura map. So those are sort of higher Shimura maps. And this is what we are studying now, among other things, especially in connection to the conjecture of Paris and Gauche. Okay, so I think I'm going to stop here. Thank you very much for your attention.